this scenario, the weld current most likely took the following path. Firstly, weld transformer primary winding, where the weld current initially flows from the transformer's primary winding to its secondary winding. Secondly, workpiece ground, because per-grounding of the workpiece allowed weld current to leak out into the surrounding equipment and structures. Thirdly, metallic conduit or cable tray, where some of the leakage current may have traveled through the metallic conduit or cable tray holding the control circuit cable. Fourthly, number 16 ground wire. The number 16 ground wire, being connected to equipment ground, provided a convenient low resistance path for the weld current to flow back to the transformer's primary winding. And fifthly, high current density, because the high welding current flowing through the relatively thin number 16 wire caused it to overheat and burn its insulation. Several factors can contribute to ground wire damage, including high weld current, where the amount of weld current leaking out was excessive, which could be due to insufficient grounding, poor workpiece contact, or a fault in the welding equipment. Also, a thin ground wire, because the number 16 ground wire was not designed to handle high currents, along with proximity to the weld area, where the control circuit cable is located too close to the weld area, exposing it to stray currents. To prevent similar incidents in the future, consider the following measures. Firstly, ensure proper grounding of the workpiece to minimize leakage current. Secondly, use heavy ground wires in areas where welding operations are performed. Thirdly, keep control cables and other sensitive equipment away from welding zones. Fourthly, provide electrical isolation between welding circuits and control circuits. And fifthly, regularly inspect and test grounding systems to ensure their integrity.